Intuitive concept of continuity. Hello everyone. Today, we are beginning our discussion on a core pillar of calculus. As you can see on the first slide, in the study of calculus, the concept of continuity is fundamental. It is a prerequisite for understanding many of the advanced topics we will encounter later, such as derivatives and integrals. Now, it is often tempting to jump straight into complex equations. But before delving into rigorous mathematical definitions and formulas, it's essential to understand what continuity means intuitively. Our goal for this session is to first build a conceptual feel for how continuous functions behave, which will make the formal mathematical proofs much easier to grasp as we progress through the following slides. What is continuity? Now that we have established the importance of continuity in our introductory slide, let's move on to defining what it actually means in a conceptual sense. Informally, we can say that a function is continuous if it behaves in a predictable manner. To explain this further, in a continuous function, a very small change in the input value, x, results in a correspondingly small change in the output value, f of x. In other words, the output doesn't react violently or erratically to a tiny nudge in the input. Because of this predictability, there are no sudden jumps, breaks, or holes in the behavior of the function. It flows steadily. To put it simply, if you move a tiny distance along the x-axis, the value of the function should not suddenly leap to a completely different value. It should transition smoothly from one point to the next. Now that we have this intuitive grasp of predictability, let's look at how we can actually visualize this on a graph in the next slide. The graphical interpretation. Now that we have established the general idea of predictability and how small changes in input affect the output, let's move from the abstract concept to a visual one. The most effective way to understand continuity is to visualize it through the graph of a function. To do this, we can use a very simple method known as the pen test. Imagine you are drawing the graph of a function on a piece of paper. If you can draw the entire curve over a specific interval without ever lifting your pen off the page, then the function is continuous over that interval. Visually, a continuous graph appears as a smooth, unbroken line or a curve that flows steadily from one point to the next. Conversely, a discontinuous graph is one where the flow is interrupted. You will notice a gap, a hole, or a sudden vertical jump. In these instances, you would be forced to lift your pen to continue the drawing, which confirms that the function is not continuous. This visual intuition provides a great foundation, but to truly grasp the concept, we need to see how it applies outside of a textbook. In the next slide, we will explore some real-world examples to compare continuous and discontinuous processes. Real-world example: continuous vs discontinuous. Now that we have discussed the visual pen test and the general idea of predictability, let us apply these concepts to some real-world scenarios to better understand the difference between continuity and discontinuity. First, let us look at example A, the temperature of a room. Imagine we are monitoring the temperature over a 24-hour period. Suppose that at 10 o'clock in the morning, the temperature is 20 degrees Celsius, and by 11 o'clock, it has risen to 22 degrees Celsius. In this process, the temperature must pass through every single possible value between 20 and 22 degrees. It cannot simply skip from one value to another. Because the temperature does not jump instantly, we can conclude that it is a continuous function of time. In contrast, let us examine example B, a digital switch. Unlike the gradual change in temperature, the state of a digital switch is binary. It is either off, which we represent numerically as 0, or on, which we represent as 1. There is no intermediate state here. The switch cannot be halfway between 0 and 1. Therefore, the act of flipping the switch causes an instantaneous jump from 0 to 1. This sudden leap is a perfect example of a discontinuous process. By comparing these two examples, you can see how continuity relates to smooth transitions, while discontinuity relates to abrupt changes. In the next slide, we will move from these real-world analogies to a mathematical example to see how we analyze these jumps using a piecewise function. Understanding discontinuity through a mathematical example. Now that we have explored real-world analogies like the digital switch, let us apply that same logic to a mathematical example to see exactly how a jump manifests in a function. Please look at the piecewise function provided on the slide. In this case, f of x equals 1 if x is less than or equal to 0, but f of x equals 2 if x is greater than 0. To determine if this function is continuous, we will follow these three analytical steps. First, we evaluate the function exactly at the boundary. When x equals 0, according to our first rule, f of 0 equals 1. Second, we observe the behavior just to the right of that boundary. If we move a tiny distance away from 0, for instance, to 0.0001, the second rule now applies, and f of 0.0001 equals 2. Third, let us analyze the change that occurred. Notice that a very small change in the input, moving from 0 to 0.0001, resulted in the output jumping abruptly from 1 to 2. In conclusion, the function is discontinuous at x equals 0. As we discussed in the previous slides, for a function to be continuous, nearby input values must result in nearby output values. Here, the values do not remain close, they leap. If you were to apply the pen test we mentioned earlier, you would be forced to lift your pen to move from the value of 1 to the value of 2, confirming a break in the graph. Keep this specific example in mind as we move toward our key takeaways and common mistakes. Key takeaways. Now that we have explored the examples and the mathematical behavior of these functions, let us summarize the key takeaways to solidify your understanding. First, regarding the intuitive definition. As we discussed, continuity essentially means that a small change in the input value, x, leads to a correspondingly small change in the output value, f of x. In other words, the function behaves predictably. Secondly, remember the visual rule we explored earlier. A function is considered continuous if you can draw its graph on paper in one smooth motion without ever lifting your pen from the surface. On the other hand, a discontinuity occurs whenever this smoothness is interrupted. This happens if there is a sudden jump, a hole, or a break anywhere along the graph, much like the jump we analyzed in our piecewise function example. Finally, to keep this grounded in reality, remember the analogy between continuous and discrete processes. Continuous processes, such as the gradual change in room temperature or biological growth, flow without interruption. In contrast, discrete processes, like the flipping of a digital switch, happen in abrupt steps. With these fundamental concepts in mind, let us move forward to the next slide, where we will discuss some common mistakes to avoid so that you do not confuse these intuitive ideas with more rigorous mathematical definitions. Common mistakes to avoid. Now that we have covered the intuitive concepts and the key takeaways, let's conclude this session by discussing some common mistakes to avoid. It is important to clear up these misconceptions before we move on to the more rigorous mathematical definitions. First, be careful not to confuse a function being defined at a point with it being continuous at that point. Simply put, just because a function has a specific output value at a point, which we can call point C, it does not automatically imply that the function is continuous there. To illustrate this, let's refer back to the piecewise example we analyzed in slide 5. In that specific case, the function f of 0 was clearly defined as 1. However, as we observed, the function was still discontinuous at that point because of the sudden jump to a value of 2. This proves that having a defined value is not enough to guarantee continuity. Secondly, avoid the assumption that all broken graphs are the same. While we have focused heavily on jumps in this introductory lesson, not every discontinuity manifests as a jump. In our upcoming lessons, you will learn that some discontinuities appear as holes, where a single point is missing from the line, or as asymptotes, where the graph curves sharply upward or downward toward infinity without ever touching a certain line. Understanding that there are different types of breaks in a graph will be crucial as we transition from this intuitive understanding to formal calculus.